In this video, we'll discuss more details of the behavior of nonlinear systems. The main thing to think about for nonlinear systems, there can be a lot of behaviors for them that don't line up what we saw for linear systems. This is one sort of base example, right? If I have two different nodal sink equilibrium solutions, for a linear system, having a nodal sink means everything flows into that solution, right? But for nonlinear, this can be an issue. If I have two different ones, say I have one over here and one over here, both these are nodal sinks, so everything should flow into them. Well, something's going to have to happen somewhere in the middle here, right? I can't have everything flowing in there because something's going to flow into here and something else is going to flow into here. And so there's going to be some difference between the general behaviors that we get because there's just multiple solutions flying around. Even if there isn't, there's a possibility for, maybe there's a solution over here that starts over here and just goes that way. It's nonlinear. Who knows? That could happen. But you can get a lot of this weird behavior because you have different terms interacting and different types of equilibrium solutions interacting with each other is going to cause some of this strange behavior. This also ties back into thinking about nonlinear equations, where we also got some strange behavior. Things like solutions stopping to exist after some amount of time. Well, that didn't happen for linear equations. Or things like non-uniqueness that we also saw, which only came about from nonlinear equations. The idea is the same here. If we make the system nonlinear and add this extra complication factor, things are going to get more involved and weird things can happen with that. And that's just the idea that this makes things more complicated. For a linear system, there's only one equilibrium solution at 0. So that one solution, the behavior around it sort of drives the behavior of the entire system everywhere. For nonlinear, there might be multiple of these, but also you can just get behavior that doesn't match the linear system because of this nonlinearity. And so things are just more complicated, more involved when you have a nonlinear system. And the main thing is, there's usually not a good way to tell what's going to happen for random initial condition unless you plot a graph or numerically solve this problem. We have a few techniques, but in general, just looking at the equation itself, you can't really tell exactly what's going to happen just based on the equation as it is. So for example, one way to do this is by looking at a slope field. So we could consider a slope field here for the following system and try to figure out what's going to happen here. So we can start by finding equilibrium solutions. Let's do that first, and then we'll go on to the slope field and see what happens. So here, for the first one, we have either x equals 0 or y equals 2. For the second, x equals y, or y equals -1 minus x. So from that, we're going to get 4 points. We're going to get 0, 0. We're going to get 2, 2. We're going to get 0 and -1. And we'll get 2 for y and -3 for x. Then we can plot these on our slope field to see how everything's going to interact here. So 0, 0 is going to be around here. 2, 2 will be up here somewhere. 0, -1 is right here. And -3, 2 is up here. Now, based on these arrows, you could also do the linearization analysis if you wanted. It looks to me like the purple point here is a saddle. I'm seeing lines that sort of come in and break away. I'm seeing a saddle sort of there. I'm seeing the same thing at -3, 2. Again, lines coming in and breaking away. Again, the same thing at 0, -1. Breaking away this way. And it looks like 0, 0 is a nodal sink because everything is sort of angling its way in somehow. You can determine this from the equation as well, but that's that. So here we have that 0, 0 is the only sink for this problem. But we can see there are some solutions, say the ones that are way up here, that are going to come in and just take off and run away. And they're not going towards that one asymptotically stable point for this equation. Right? The same thing goes for solutions up here, things that are down here that bend off this way, and same thing down here. So what it looks like is that if I sort of sketch out in orange, that anything that sort of comes in inside those orange regions there ends up being funneled in towards 0, 0 as time goes on. And this is all just sort of a guess type process. I'm just guessing based on what the slope field looks like and where the lines are sort of going to get an idea for which sort of solutions end up funneling in towards the point 0, 0. If it's outside that region, it goes away. If it's inside the region, it goes in towards it. If we zoom in on these points more individually, we can see that for the top 2 points, 2, -3, and 2, 2, I'm definitely getting a saddle type of vibe from these 2 points here. You can see it more explicitly here. right? The solution curves that sort of come in here and loop out this way. And for the bottom two, I'm getting a saddle here again, and a sink here at 0, 0. You can see this also in more detail when you zoom in on the graphs, which is what we expect because they are linearizations. They get better approximation as we get closer and closer into the actual point in question. How do we talk about these concepts? There are two main words that we use to describe these things. The first is the idea of a basin of attraction. This is the idea of if I have any point in the plane, does the solution go towards a certain sink or stable point as time goes on? So the basin is the set of all points in the plane where if I start a solution there, it will go in towards a certain sink as time goes on. Now this requires it to be paired with a specific sink that things are going to converge to. And then to go along with these, we have things called a separatrix or separatrices for plural. And these are sort of the boundaries of this basin. They are curves that divide up where solutions are going to go in time, whether they go into one sink or to another, or they go away to infinity. They sort of form the boundaries of these areas where determines which way the solutions go. In terms of the previous picture we had, the orange curves that I drew were the separatrices, and everything inside them was the basin of attraction for that sink at 0. Let's give some more information about the idea of nonlinear systems and the different behaviors they can have that are very different from linear systems, because this interaction and this nonlinearity can cause extra complications, including these basins of attractions and separatrices that are important when you want to analyze how this is going to behave and how things are going to develop as time goes on with these nonlinear systems.